In the last session we have discussed what are consistency limits, and then of them liquid limit and plastic limits are discussed. In this session I'm going to tell you about shrinkage limit. Overall, we have seen that limits are nothing but water contents represented by W. The suffixes will be indicating which limit it is, and then they are nothing but water contents. In this particular graph, which explains the consistency limits or Atterberg limits, we have on horizontal axis water content, and then on vertical axis volume of the soil. Okay, here it is written as volume of solids, but it is volume of soil. Let me write it properly. So this is volume of soil actually, right? So here there is a volume of soil. You have seen in other graph also where it is represented by A, B, C, D and all. Now this particular point we have seen that it is a liquid limit. This is plastic limit. We have discussed how to find out liquid limit and plastic limit. Now further down, when the water content decreases beyond plastic limit, the volume also decreases, and then there is a point where there will be a reduction in the water content, but there won't be any reduction in the volume of the soil. Please note this particular point. Here the water content decreases, reaches a point. Correspondingly, the volume of the soil decreases, but at some point the volume does not decrease. That particular stage, whatever water content is there, that will be known as shrinkage limit, because the soil shrinks and then stops shrinking. That particular water content is known as shrinkage limit. Here you can see in the sketches also how it is shown. Here there is only solids. Here there is a lot of water, volume is there. Now when you dry it, what happens is the volume will be maintained, but the water content decreases. That is the stage somewhere there. There is water content and it is decreasing, right? It has reached at this particular point. This figure corresponds to a point there. When water decreases, means water evaporates, but the volume is not decreasing. And when you come to this particular point, all the water is vanished, but the volume is still remaining the same. So that is what is indicated in stage 3, right? Anyway, in words, if you want to define shrinkage limit, it is the water content corresponding to an arbitrary limit between semi-solid and solid states of consistency of the soil. Semi-solid and solid state, it is between them. It is the lowest water content at which the soil is fully saturated. Yeah, see, this is the water content at which it is fully saturated, right? And then if you add more water, obviously it is saturated. If you decrease the water content, there will be voids created. Because of that, it will not be fully saturated. So this is the minimum water content or the lowest water content at which the soil is fully saturated. That is a good definition, but you should understand the meaning of it. Now, it is also the maximum water content at which any reduction in the water content will not reduce the volume of the soil. Look here, when this particular point, if you increase the water content, there won't be any increase in the volume, right? It is also maximum water content at which any reduction in the water content will not reduce. Now, if you take any point here, if there is a reduction in the water content, there will be reduction in the volume. But this particular point, if you decrease the water content, volume will not decrease. So it is the maximum water content at which corresponding decrease in the water content will not cause any decrease in the volume. Very interesting. If you can understand, it's well and good, right? Please discuss with your friends if you don't understand, but make sure that all these limits are properly understood, especially the shrinkage limit. Okay, we'll go to the next slide. How exactly the shrinkage limit is found in laboratory, that is shown here. So this is a set of equipment that you require for conducting shrinkage limit. What you have is a measuring flask, shrinkage dish, a glass cup, and then there is evaporating big bowl, and there is a plate with three prongs, that is a pin like arrangement which will be protruding out of the glass plate, which will be put on the top as shown in this sketch. Okay, now what is the procedure? I'll tell you the procedure. I don't know whether written here. No, I'll tell you the procedure. In this shrinkage dish, the soil slurry, what I mean by soil slurry is you have to take the soil which is passing through 425 microns. Keep remembering, because in almost all the Atterberg limits or consistency limits, the soil has to be taken which is passing through 425 microns. So take some amount of soil which is passing through 425 microns, put water, the water which is sufficiently more than the liquid limit, means the soil is in slurry state or it will be freely flowing, and such slurry is poured into this dish, and that is what is shown here. So the container over here is nothing but this shrinkage dish. This is soil with a lot of water. Now this is weighed, and the weight is W, or you can call it as M, the mass, but here it is taken as W, fine, W. The volume of this shrinkage dish you can find out, V, volume of this. How to find, we'll see it afterwards. You can measure it also, anyway it is perfectly cylindrical, but there is a way out, I'll tell you. So volume of the soil is V, weight of the soil is W. How to find out weight of the soil? Soil plus container, you can take the weight, minus empty container will give you mass of the soil or weight of the soil. That is written here. Okay, now this dish is shown over here also, wet soil shrinkage dish before shrinking. This is the stage. Now this is first of all kept in air for an hour or so. It is dried a bit, and then afterwards it will be transferred to oven, and it will be dried overnight. And then after 24 hours, when you come back and take out the dish, what happens is the soil gets converted into a fine cake, like a dry soil pat we refer it as, and it will be shrunk in volume. So after shrinking, it will be into a soil palette like that. There is a shrinkage dish in which the shrunk soil pat would be there. Now we should be able to find out the volume of dry soil pat, right? Soil volume is VD, and then soil weight is WD, because it is a dry weight of the soil or weight of soil solids only. That's what it is. You can find out that. Now once you know all these four values, here I have written them. W, the initial weight of the soil, here it is. WD, the dry weight of the soil, over here it is. Phi, the initial volume of the soil, that is shrinkage dish volume. Phi D, dry volume of the soil, that is volume of the soil pat. Gamma W is the unit weight of water. Then shrinkage limit is given by simply W minus WD minus Phi minus Vd into gamma W divided by WD. This is the shrinkage limit. Now the question is how to find out the volume of shrinkage dish as well as volume of dry soil pat. Masses can be found using the balances, but how to find out the volume, that is an interesting part here. In this bowl, which is shown here, evaporating dish in this, so what is done is this glass container, glass cup, you can just see here, this glass cup is put into this, and then full mercury is poured into this, exactly leveled off with this plate putting on top of it. Whatever extra mercury that has fallen can be taken back, so that you have a glass cup which is full of mercury. Now what you do is, whatever dry soil pat is there, you put on top of the mercury, here mercury, and then because the specific gravity of mercury is quite large compared to the specific gravity of the soil pat will be floating on top of mercury. Now what you have to do is, using this plate, you have to push it down into the mercury and then up to the level. So that is the top of the cup, and then that is the glass plate with prongs, which will be helping you to push the soil pallet into the glass cup. Now what happens is, when you push it down equal to the volume of soil pat, the mercury will be coming out. So mercury displaced by the soil pat will be falling into the dish. Now you take out the plate, take out the soil pallet, so take out the dish also. So whatever collected mercury is there, the mass of that will be taken, divided by the mass of the mercury divided by density of the mercury, will be giving you volume of the mercury, which is nothing but volume of dry soil pat. So mercury is used for finding out the volume of dry soil pat. So that's how Vd is found. Now once you know all these four quantities, you can work out shrinkage limit. That's how the procedure is, and then you should remember the formula. Okay. Now consistency or upper limits, to revise everything in one go. Whenever you define consistency limit, you make sure that you will be plotting this graph, water content and then volume. You will be having a curve like that straight down, starting with point A, B, C, D, and then at D it goes horizontal. That is the minimum volume of the soil. The stages are, beyond this B we have liquid state, between B and C we have plastic state, between C and D we have semi-solid state, and then this horizontal stretch will be having solid state. Now corresponding water contents at B, at C and at D are liquid limit. It is limiting water content of liquid state, limiting water content of liquid state, that's why it is liquid limit. Then water content decreases, then there is a limiting water content of plastic state, that is plastic limit. Further down it shrinks and then it stops shrinking. That particular water content is known as shrinkage limit. That's how you can explain. We'll continue the discussion of consistency limits. Now it is consistency indices we are going to define. Okay, let's straight away go ahead. The first index that we are going to define is plasticity index. Because it is an index, it is represented by capital I, and plasticity index, that's why there is a suffix P, plasticity index. Now before defining plasticity index, let me tell what is plasticity. It is the property of the soil that allows it to deform rapidly without rupture. Plastic, obviously it doesn't break, it doesn't show any crack, right? Elastic rebound without rupture, without elastic rebound, and volume change, without volume change. So it is the property of the soil that allows it to deform rapidly without rupture, without elastic rebound, and without volume change. That is what is plasticity. If it rebounds back, it is elasticity. So it is in plastic state, it doesn't come back if you give a deformation. So why this plastic character comes to the soil, it is said in just one words. Of course we'll be throwing more light on this aspect, but at the present just keep this in mind. The thin film of water adhering to clay particles is responsible for its plastic behavior. I assure you that we'll be talking in detail about this particular aspect of plastic characteristic of soil when we discuss clay mineralogy in the next module, right? So very concisely in a sentence it has been given that a thin film of water which is attached to the clay particles is responsible for the plastic characteristic or plastic behavior of the soil. So you should make a note here. It is not the soil which takes the credit, but on the top of soil particles, whatever water layer is there, that takes credit, and then it gives the soil a plastic character. Anyway, plasticity is characteristic property of the soil, and it comes into action only when there is water on it. Okay. Now plasticity index. Now this is easy to understand because plasticity index IP, it is the difference between liquid and plastic limits. Very simple. We have defined what is liquid limit and then plastic limit. If you take difference, whatever value you get, that is called plastic limit. Plasticity index. A soil with IP equal to 0 is called non-plastic, means this minus this equal to 0, in the sense there is no plastic state at all. Obviously all the coarse grain soils will not have any plastic state as such. Because of that they are non-plastic, they don't have any plastic state, and it is represented as NP, non-plastic. Higher the values of IP, more plastic will be the soil. Okay, IP is nothing but WL minus WP. It is the range of water content in which the soil is in plastic state. Let me tell you, a value of WL is equal to say 50 and WP is equal to, let us say, 40. Here it is 50%, here it is 40%. So 10% of water content is a window in which the soil will be behaving like plastic. That too, above 40% water should be there, and then it should not go beyond 50%. If it goes beyond 50%, it will be liquidish, it will be flowing, it will not be plastic. But if it decreases less than 50, and then if it is more than 40, then it will be showing a plastic state. Now say there is one more soil wherein liquid limit is 50 and plastic limit is say only 10. Then you got a window of around 40%. Here it is 50, here it is 10%, means 40% of range in which the soil is in plastic state. It is a good range, because what happens is there is you can allow it to dry from 50 to 40, 30, 20 till 10. It will be still in plastic state. There is no fear that immediately after little bit of drying it will be entering into semi-solid state. That is the meaning of plasticity index. More the value, it is more plastic. That's what one can say. Next, there is consistency index and liquidity index. There are two indices which are defined. Very simple. Look at these two equations or expressions here. Consistency index is WL minus W, liquid limit minus natural water content. This is divided by IP, the plasticity index. So consistency index, it is the ratio of liquid limit minus natural water content to plasticity index of the soil. The same thing is put in the form of expression. Okay, consistency index, it is the ratio of liquid limit minus natural water content to plasticity index. It is represented by an equation also over here. IC is equal to WL minus W divided by IP. But what is IP? We know that it is WL minus WP. So it is simply, consistency index is WL minus WP, WL minus natural water W divided by WL minus WP. So it compares this water content to the plastic limit. Okay, so one can analyze by this that if W is the natural water content, when IC is less than 0, when IC will be less than 0, when WL is less than W. Here if you see, W natural water content is more than the liquid limit. This natural water content has to be more, so that this will be negative. Then IC will be less than 0. So water content will be more in the sense the soil is in liquid state. So when IC is less than 0, the soil is in liquid state. Very nice. Now when IC is equal to 0, when IC will be equal to 0, WL and W are equal. So to say, the soil is at liquid limit. The soil is at its liquid limit. When IC is equal to 1, when IC is equal to 1, WL minus W is equal to WL minus WP. So to say, W is equal to WP. The natural water content is at this point. So to say, when IC is equal to 1, the soil is at its plastic limit. And when IC is greater than 0, when it will be greater than 0, WL is more than W, that is 1 point, and then W should be less than WP. W should be less than WP, means somewhere there. Then that is to say, semi-solid state or even stiffer state. So when IC is greater than 0, the soil is in semi-solid state and beyond, and it is stiff. Hence, more the value of IC, the stiffer will be the soil. Lesser the value of IC, right? It is lesser the value of IC. It will be in liquid state. It moves on this side. Lesser the value of IC, it goes this way. More the value of IC, it comes this way. And then by putting IP equal to WL minus WP, one can analyze for all these values of IC. Rather than remembering them, the logic behind that has to be understood so that you will not get confused. Similarly, the Definition of liquidity index, I with a suffix L, it goes this way. It is the ratio of natural water content minus plastic limit, W minus WP, to plasticity index of the soil divided by IP. But we know that IP is WL minus WP once again. Okay. Now again you can analyze in the similar manner. Here W is the natural water content. When IL is equal to 1, the soil is at its liquid limit, obvious, because this will be equal to this, in the sense W will be equal to WL at its liquid limit. When IL is equal to 0, the soil is at its plastic limit, and when IL is less than 0, means natural water content is less than plastic limit, the soil is in semi-solid state and beyond, right? Hence, more the value of IL, softer will be the soil. More the value of the soil, more the value of IL, softer will be the soil. Here, more the value of IC, stiffer will be the soil. Look at that. So that is the drastic difference between consistency index and then liquidity index. Okay. Next, there is flow index, IF. Flow index. First of all, we'll see what is flow curve. Flow curve is a plot between moisture content and number of drops to close the groove in Casagrand's test of liquid limit. Yeah, we have discussed liquid limit by Casagrand, in which water content is plotted on y-axis, and along x-axis in log scale we plot number of drops, and you get number of points. We join it with a straight line to find out what is the water content. Actually, we search for this value of 25. We go up the curve that way, go to this point, and then search for the value of liquid limit, that is the water content corresponding to 25 number of blows is defined as liquid limit. Here there is 1% given, 35.2 as the example, one value of liquid limit. It can be anything. Okay, so this curve, whatever straight line you get, we call it as flow curve. Please make a note. What is meant by flow curve? It is nothing but the curve that we get in Casagrand's liquid limit test. Now, what is flow index, IF? It is the slope of flow curve, simply. Now you take any 2 points on the curve, make a triangle, y by x will be giving you the slope of the curve, and that is nothing but IF. You can just see here W1 minus W2. Say this is W1. Now let me show it here. So this is W1. Okay. Now corresponding to this particular point, let's say this is W2. Now W1 will have its own value of N1. Here there is a value of N2, number of drops. So anyway, this is log to the base 10. So you have log of N2 by N1, means log N2 minus log N1 to the common base 10. That's why this expression comes. So it is nothing but slope of the flow curve, that is known as flow index. Okay. Next, there is what is known as toughness index, IT. The toughness index, which is represented by capital I with a suffix T, it is the ratio of plasticity index to flow index. Very simple definition. IT is equal to IP by IF. You know, plasticity index is nothing but WL minus WP. In all other indices, this used to go in the denominator. but it is coming in the numerator when it is a definition of toughness index. So IP divided by IF we have already just now defined. So it indicates the stiffness of the soil. Toughness index obviously indicates the stiffness of the soil. More the toughness index, greater will be the stiffness and resistance to deformation of the soil. That is what is indicated by toughness index. So density index, this indicates the denseness. Already we have defined density index ID equal to Emax minus E natural divided by Emax minus E minimum. The range of values of ID, how to identify that is, observe that Emax and E minimum are determined in the laboratory. This has been already discussed. If the soil is very compact in its natural state, then what happens is E natural will be E minimum. Compact in the sense voids are less, that's why E will be minimum. So E natural will be equal to E minimum. E natural will be equal to E minimum. Because of that, the ratio becomes 1. So if the soil is very loose in its natural state, E natural becomes E maximum. So when it becomes E maximum, this becomes 0. Hence ID will be equal to 0. So what is the conclusion? The value of ID nearer to 1 or 100% in percentage indicates denser state, and value of ID nearer to 0 or 0% indicates looser state. Okay, here the table gives you the descriptive words for different values of density index. If ID is less than 35%, means less than 0.35, we can say that the soil is loose. And then if the value is between 35% and 65%, that is ID equal to 0.35 to 0.65, then we can describe it as medium dense. And then if the ID is between 65% and 85%, then it can be described as dense. If value of ID is more than 0.85, that is more than 85%, then it can be described as very dense in its natural state. Okay, next we have Skempton's activity number, or it is simply referred to as just activity. What is it? It is defined as the ratio of plasticity index to the percent of clay size particles in the soil. If the same thing is put in the form of expression, AC activity number is equal to IP plasticity index divided by percentage finer than 2 microns. Means in the soil you have to find out the particles lesser than 2 microns, that is percentage of the particles which are lesser than the size of 2 microns. That has to be kept in the denominator. This ratio is known as activity. This is an indicative of swelling potential of expansive soils. Expansive soil means the soil, when it comes in contact with the water, it expands. The best example would be black cotton soil. When you put the water onto that, it swells, it expands in its volume. But when it is dried, it shrinks in its size. So similarly, activity for Montmorillonite clay, of course these three names will be coming across in the next module as clay minerals. So activity for Montmorillonite clay is of the order of 7.2, whereas for illite it is of the order of 0.9, and for kaolinite it is 0.38. Now how do you make out from these numbers what it means? Here there is a chart. Activity number less than 0.75, it is inactive, means it is good quality soil, we can say, right? If the value is between 0.75 and 1.4, it's normal, it's okay. But if the value is more than 1.4, then it is quite active. So this is a dangerous soil on which you can build any structure, because sooner it comes in contact with water, it expands enormously. And look at the value of 7.2, very dangerous. Okay. Okay, thank you. Stop here.